Hello everyone, we are on to the next part of hydrocarbon, and in today's session we will be talking about benzene, its structural aspects and the preparation of benzene. Right, now if you see the molecular formula of benzene is C6H6, and if you compare it with C6H14, that is hexane, which was a saturated hydrocarbon. Hexane is a saturated hydrocarbon. If you compare with that, the molecular formula, it implies that this should be highly unsaturated. It should be highly unsaturated. Right? Because you can just check the number of the carbon hydrogens. The hexane is following that CnH2n plus 2. So it is having 2 more than the double number of hydrogen atom, but this is having less number, so that means it should have unsaturation. It is having unsaturation, though it is supported by some reactions. Like first, if you take benzene C6H6, it can react with 3 hydrogen molecules in the presence of nickel, and on heating it results in the formation of C6H12. That means benzene forms a cyclohexane. It indicates that there must be 3 double bonds. So where 3 H2s can add on, and it results in the formation of cyclohexane. This reaction proves it is having unsaturation. Second, that if you carry out the reaction of benzene with chlorine in the presence of sunlight, then what it forms is C6H6Cl6. That means it forms benzene hexachloride. This also indicates that 3 chlorines would have added, and all double bonds have disappeared, and there are only single bonds, and all carbon atoms have chlorine. The third reaction is, if you react benzene, it can add on to 3 ozone, and it will form benzene triozonide, that is C6H6O3 taken thrice. That means before hydrolysis part. So it will form benzene triozonide, and we know that ozone adds on to the multiple bonds. So it forms benzene triozonide. All these 3 reactions indicate that there are 3 double bonds in them, in benzene. That means there is unsaturation. So though it is having pi bonds, it is not behaving like unsaturated carbon compounds. It is behaving more like saturated compounds. Benzene behaves more like saturated compounds. Now, what reactions prove that it is behaving more like these saturated? It undergoes more substitution reactions than addition reactions. It undergoes more substitution reactions. For example, if you take benzene, carry out the reaction with bromine in the presence of carbon tetrachloride, it will not add on. You will not have this Br2. You will not have bromine added on to the double bonds. So this reaction is not given. This reaction is not given with benzene carbon tetrachloride, is not given. But if you carry out the reaction of benzene with the bromine in the presence of Lewis acid, FeBr3, then it will form C6H5Br plus HBr. This is a substituted product. It is substituted product. That means it is carrying out more substitution reactions than the addition reactions. Though these reactions, first 3 reactions prove that there is multiple bond present, means it's behaving more like unsaturated, but most of the reactions of benzene are like saturated compounds. So what is the actual structure? Let's focus upon that. Yeah, before that, one more thing. Benzene is resistant to oxidation. Benzene is resistant to oxidation. Like in alkenes, we have done the reaction, it undergoes reaction with alkaline KMNO4, right? So benzene cannot react with alkaline KMNO4 or potassium, potassium dichromate, whatever. So any oxidizing agent, if you are reacting with benzene, it will not be undergoing any kind of oxidation. It's resistant to oxidation like saturated hydrocarbon. So what is the actual structure of benzene? Actually in the beginning various structures were given, but finally this structure of benzene was accepted. This is proposed by Kekule. There are all carbon atoms have one hydrogen. This is referred to as the Kekule structure of benzene. Kekule structure. Though Dewar structure was there, Claus structure, Bayer structures were given, but this is the final structure which was proposed by Kekule. Though this structure also there were some objections given. Like for example, this is one structure where I have put the double bonds like this. So another structure of the Kekule also can be drawn with all the carbons again having hydrogens, and the position of the double bonds are now different like this. So the position is different. So these two were equally existing structures. So it was said that there is dynamic equilibrium. There is dynamic equilibrium between the two structures of Kekule, where the position of the double bond is not fixed. It can be even this way. You can write down either this way or the other one. Okay. Now let's see the molecular orbital structure. Molecular orbital structure of benzene. Now molecular orbital structure of benzene says that every carbon atom in benzene is undergoing sp2 hybridization. sp2 hybridization means on the carbon atom, the three hybrid orbitals which are there, they are arranged in the trigonal planar manner. Trigonal planar geometry. These three sp2 hybrid orbitals are arranged, and the bond angle on each carbon atom is 120 degree. Let's draw the structure of this. First, I'm just drawing 6 dots to represent the carbon atoms, and on them now hybrid orbitals. One sp2 hybrid orbital, second sp2, the third sp2. Okay, that small lobe of the hybrid orbital, no need to draw. We can ignore it because this will give you a better understanding. This is one carbon atom, 3 sp2 hybrid orbitals. Second carbon atom, 3 sp2 hybrid orbitals, second one and third one. For the next one also, sp2, sp2 and sp2. sp2 hybrid orbital, sp2 and sp2. For the fifth one, like that you can have. For the sixth one also you can have like this. Okay, and just see how the bonds are being formed. On each carbon atom there are 3 sp2 hybrid orbitals, of which 2 of them are overlapping with the neighboring 2 sp2 hybrid orbitals of the carbon atoms, and the third one is overlapping with 1s orbital of hydrogen atom. So we can say that each carbon atom is forming 2 sigma bonds with the neighboring sp2 and 1 sigma bond with hydrogen. So overall if you are checking, there are 6. This is 1, 2, 3, 4, 5, 6. There are 6 sigma bonds. Which categories? Carbon-carbon. That is sp2 of one carbon overlapping with sp2 of the next carbon. 6 sigmas further are between carbon and hydrogen, where sp2 of carbon is overlapping with s of hydrogen. The bond angle here is 120 degree and the shape is trigonal planar. Is this point clear? The total number of the sigma bonds are 12. 6 of one type and the 6 of the another type. Apart from that, we know carbon is tetravalent. That means there is one more p orbital over it. So that I am drawing on the next slide. Now just observe this. We can draw them like this because sigma bonds are all in one plane. The pure p orbitals present on each carbon atom will be perpendicular to the plane like this. They will be perpendicular. So these are the pure p. I have just shown you this way. Okay, the pure p orbitals are perpendicular to the plane. Now how these pure p orbitals can overlap? This pure p orbital can overlap with this side or with this side carbon atom. So suppose this pure p of one carbon overlaps with this carbon sp2, pure p orbital. Same with this, these two pure p orbitals overlap or these two overlap. Or it can be even this way, if these two are overlapping, these two are overlapping, or these two are overlapping. So what are you concluding in this? You are getting two different structures of benzene, wherein in the first case these three are the pi bonds, in the next case these three are the pi bonds. This is what we spoke about in the beginning, that these are the pure p orbital. There are two possible structures of Kekule. These are the two resonating structures of the Kekule. Okay, now actually with this what we conclude is the pure p orbitals which are present above the plane and below the plane, they can form a delocalized electron cloud. We can just show this way. There can be delocalized electron cloud above the plane and below the plane. Above the plane and below the plane there is a delocalized electron cloud because the pure p orbitals can overlap this way or it can overlap this way. So if this is the benzene ring, the electron cloud which is there will be above the plane as well as below the plane. So there is delocalized electron cloud present in benzene. So due to which what happens is, you find that in benzene, because of delocalization, due to delocalization of the electrons above and below the plane, what you find is the bond length. Which bond length? Carbon-carbon bond length in benzene. You find that carbon-carbon bond length in benzene is 139 picometer. And all carbon-carbon bond lengths in benzene are equal. Okay, they are all equal, and all carbon-hydrogen bond lengths are 110 picometer. They are also all equal. Unlike the carbon-carbon normal single bond length 154 picometer or the normal carbon-carbon double bond. It is neither equal to the carbon-carbon single bond nor equal to carbon-carbon double bond. You find that all carbon-carbon bond lengths in benzene are equal. What reason? This can be a very important reason question asked. Why, or it can be given, are all the carbon-carbon bond lengths in benzene equal? Explain. Or they are equal, give reason, though it is having alternate single and double bonds. So you will write down on the basis of delocalization of electron cloud. So which makes all the carbon-carbon bond lengths in benzene equal, that is 139 picometer. Okay, and one more thing is that the dipole moment in benzene is 0. So it does not show any type of isomerism. Now moving on to preparation of benzene. So if you go by your NCERT book, there are three main methods given. One, from ethyne, which we have already done in alkyne chapter, by polymerization, cyclic polymerization of ethyne, passing through red hot iron tube or copper tube, you will get benzene. The second method they have given is decarboxylation. Decarboxylation can be done of sodium salts of the acid. So in this case, what you take is sodium benzoate, because we are aiming to prepare benzene. So you'll have to take the sodium salt of benzoic acid. So this is C6H5COONA. This is sodium benzoate. Sodium benzoate when you carry out decarboxylation, and decarboxylation is done in the presence of soda lime, NaOH and CaO. So what you get is this part coming out as sodium carbonate, and apart from that what you have is benzene. So benzene can be prepared by decarboxylation of sodium salt of benzoic acid. This is the second method. The third important method to prepare benzene is reduction of phenol, C6H5OH, phenol. What you have in this is that this is phenol, benzene ring, and on that if you have OH, if you heat it in the presence of zinc, zinc has affinity for oxygen, it will form zinc oxide, and apart from that what you get is benzene. So reduction of phenol will give you benzene. Clear? So with this we have completed the structure of benzene and the preparation of benzene. Okay, so in the next video I will be completing the chemical reactions of benzene. Thank you.